Hello everyone. This is Marco Silveira, and it's a pleasure to introduce today's speaker, Clare Watt. Clare did her PhD at the University of Cambridge and at the British Antarctic Survey, focusing on wave-particle interactions at Magnetosphere connection sites. She graduated in early 2002 and moved to Edmond to work with Robert Rankin on wave-particle interactions in low-frequency waves and auroral acceleration. Working in the space plasma group at the University of Arizona from 2002 to 2013 gave to her a deep appreciation of the role of ULF waves in the Earth's magnetosphere, and has inspired lots of interesting work since. In 2013, she took up a permanent position in the meteorology department at the University of Reading in the UK. There, Dr. Watt expanded her research into radiation belt physics and learned a great deal from her atmospheric colleagues about modeling, forecasting, and stochastic methods. And just last week, she moved to Northumbria University in Newcastle upon Tyne, where she is now a professor in space plasma physics. Running through all her research is the theme of wave-particle interactions, so we can expect some of that in her talk. So before we begin, I'd like to remind you that this presentation is being recorded. Please keep your voice on mute, and if you have any questions, please post them in the chat box. For those attending on YouTube, you can find the instructions to send the questions in the video description. I will have to read all the questions at the end of this presentation. Okay, we can start. Dr. Watt, please proceed.
Thank you very much, and hello everybody. It's a real privilege to be able to give this seminar in this amazing seminar series on different aspects of magnetospheric physics. And today I will be talking about auroral physics. Specifically though, my brief was to talk about those aspects of auroral physics that interest me. And so you'll find out that auroral acceleration mechanisms interest me, wave-particle interactions interest me, and how all this relates to magnetospheric substorms is also something that interests me. So I like to put the acknowledgements for talks at the beginning, just in case I don't get to them at the end. And I've got many thanks here to various collaborators and co-conspirators I've had over the years. Johnny Ray, Nadine Calmoni, Cal Murphy, Robert Rankin, Colin Forsyth, Andy Smith, John Sampson, Gordon Rostocker, Bob Lysak, and David Knudsen. Conversations with every single one of those people have helped me to identify interesting problems in auroral physics and perhaps how to solve them. But none of these auroral physics problems can be solved without a great amount of data that have been obtained by many amazing teams. And so I just wanted to also mention the NASA FAST mission teams, as well as the Themis team, the Canadian Geospace Monitoring team that is now Geospace Observatory Canada, the ESA Cluster Mission team, and a special shout out to the Canadian Space Agency EPOP mission team. I started my first postdoc as part of the EPOP mission team, and there were a great bunch of people to work with. My other disclaimer for this talk is that my references are not exhaustive. Clearly, there's a huge amount of auroral physics research out there. I am trying to point out especially some great reviews that have just been published this year on auroral physics, but do feel free to contact me if there's something you want to talk about more. So I'm going to start with a video of the aurora that has been obtained from the International Space Station. So some of these videos you can find on the NASA website. They're amazing. I love this one in particular because you can see many aspects of the aurora that I find interesting. So first of all, you'll notice that the aurora glows red at the top and sort of green and white down below. You can see all the different shapes in the aurora. There's some very clear and bright, discrete shapes to the north or to the right of the image here. And there are much more fuzzy, cloudy, dim features sort of to the left of the image. And you can see the time evolution of the auroral forms. They're not static. Some of them to the left of the image are flashing on and off. Some of the auroral forms that we'll see when it loops around again that are to the right of the image, those bright auroral forms look like they're forming into twists and vortices and things like that. And I love all of these aspects of the aurora. The time evolution of it especially is something that fascinates me. I love the shapes that it makes. I love that it makes different shapes in different parts of the sky. And so what I want to talk about today is part of that. Now, I will admit that I have my own biases like any other scientist. And as was mentioned in the introduction, thanks for that, Marcos, I spent 11 years at the University of Alberta, which is where I did most of my auroral science. And so as a result, my view of the aurora is very much colored by that. So you'll hear a lot about ULF waves. You'll hear a lot about substorms. You'll hear a lot about field line resonances, because those are the kind of things that we were interested in at that time. And you can see the list of names there. Those are the people that I was having conversations with every day. And so their ideas and thoughts have influenced me greatly. But basically this slide is sort of saying my own particular scientific obsession is quite obviously waves. The word art that you can see on the right there is created from all my abstracts from the time that I spent in Canada. And you can see that waves really do feature quite prominently. And waves and wave particle interactions are really where my scientific focus are. So this seminar is going to be about auroral physics from that very specific perspective. So I'm going to talk a bit about fundamental auroral physics. If you've never really thought about auroral physics before, hopefully I'll be able to tell you a few things that'll help to pique your interest. I'll talk about the shape of the aurora, the morphology of that aurora, the acceleration mechanisms that we think are leading to the aurora, and specifically, as I say, this is my own biases, but how auroral acceleration is connected to substorm onset. And then I'll just end with a few of my thoughts on future directions and things that we really need to do before we can answer some big questions. So, fundamental auroral physics. These are the things, if you like, we know, and we're quite happy that we know. So we know that auroral displays result from collisions. These are collisions between energetic electrons and protons that were in the magnetosphere but have lowered their mirror points such that they can collide with atmospheric neutrals. So they might collide with atmospheric oxygen atoms. They might collide with atmospheric nitrogen molecules. They might collide with nitrogen molecules and create nitrogen atoms and collide with them. And what happens in these collisions is that the energy that the electron and the proton had, which can be in the keV or more range, that excites the neutral atom or molecule. And as a result of that excitation, the atom or molecule needs to release some energy, and it does so in the form of light. The color of light that it emits depends on the sort of collision that it's had or the type of atomic constituent that it is, whether it's oxygen or nitrogen. So you get the different colors of the aurora at different heights. As we saw from that original movie there, the red aurora is happening at quite high altitude and the green aurora is happening underneath. And so that's telling us that the types of collisions that are happening are different. That red line is happening from collisions that electrons are having with oxygen atoms. The green line is happening because of collisions with oxygen atoms that are happening at higher energies. And then the collisions with the nitrogen molecules and the nitrogen atoms are happening even lower down. And they're giving more like purple, violet type colors. So different energies of electrons, and I will be focusing specifically on electrons. I'm not a proton aurora person. I believe you're getting some information about, or we're getting some information about that next week. But the collisions that are happening between electrons and the different atmospheric constituents are happening because the electrons have different energies. And different energies reach different heights. So the higher energy electrons can penetrate lower through the atmosphere than the lower energy electrons. And again, when I'm using terms like high energy and low energy, it's all relative. So when I say low energy, I mean things like 100 eV or 1 keV, thereabouts. And when I'm talking about higher energies, I'm talking about energies greater than 1 keV, things like 10 keV, that sort of thing. And as I say, the higher the energy an electron has, then the further down in the atmosphere it can penetrate. So the two plots that you can see on the right-hand side are just results from modeling how far an energetic electron can get in the atmosphere. So remember, they're coming down from above. So the 100 eV electrons are really reaching altitudes of about 200 kilometers or so, and that's what produces the red aurora. And then the higher energy electrons that are maybe more like 1 keV are getting further down towards somewhere between 150 and 200 kilometers, that kind of thing. And the point is that the altitude of the collisions also depends upon the sort of constituents of the thermosphere and ionosphere, the background plasma parameters. And so panels A and B that you're seeing in this plot here have different thermosphere parameters. They're happening for different activity levels. And so the penetration depth might get changed as a result of that. And I have a reminder on this slide that we should not forget secondaries. These are high energy electrons that have had collisions with atmospheric neutrals, but they still have sufficient energy that when they go on to have other collisions, they can still excite atoms. And we shouldn't forget that those interactions are happening in the upper atmosphere. But my main interest in the aurora is not to do with the ionospheric or thermospheric physics that's related to the collisions, but using the aurora as a remote sensing tool. So they're basically providing us with this ionospheric window into processes that are either related to magnetosphere-ionosphere coupling or are intrinsically magnetospheric. And that's my interest in sort of why I'm interested in auroras. They give us this opportunity to remote sense what is happening in the magnetosphere. And I put this slide in just to remind myself I had to mention it. I am only interested in electron precipitation. I've never really studied proton precipitation, although it was really, really interesting. So everything that happens from now on in this seminar will be related to electron precipitation and the physics that can promote that electron precipitation. So next, I'm going to talk about the shapes of aurora, the different kinds of aurora that you can see. So here's some examples, and this is the list of things that I'm going to talk about in a bit more detail. I'll talk about auroral arcs, field-line resonances, polar cap aurora, patchy aurora, which is related to pulsating and flickering aurora, and some substorm aurora. And the images you can see on the right in this slide are images from the NASA Themis ground-based segment, which is a mosaic of all-sky imagers in Canada and Alaska, showing us the aurora with unprecedented detail over a large portion of the sky, a large portion of magnetic local time. And you can see a number of different shapes. So there's just some examples there, but you can see ripples, you can see arcs, you can see repeating patterns, you can see mixtures of different types of aurora in the same image. And some of the terminology I will be using in this seminar is the idea that some aurora are discrete and some are diffuse. And I'm hoping to use this picture to try and explain the difference between a discrete and diffuse aurora. So I guess at one extreme of the scale, you have discrete aurora, which are very bright. They form well-defined shapes. You can see arcs, which are long, thin ribbons. You can see ribbons that might show vortices, but you can see very definite shapes. The diffuse aurora, on the other hand, are sort of at the other end of the scale. They're much dimmer. They're perhaps a little fuzzier. They don't have well-defined structure, although there is some structure in there. And they tend to, at least in this image, the discrete aurora occur on a very small portion of the sky, whereas the diffuse aurora cover a much larger area. Now, I can't give you a threshold. I can't say that aurora above this brightness are definitely discrete and aurora below that brightness is definitely diffuse. And this idea that discrete have structure whereas diffuse don't is maybe not exactly correct. There is definitely structure in the diffuse aurora. And the discrete aurora can also be quite large as well and cover a large portion of the sky. But in general, discrete is bright and sharp whereas diffuse is dimmer and a bit more fuzzy. So auroral arcs are the classic discrete auroral shape. They're observed throughout the auroral oval and they are relatively stationary. The one time I was lucky enough to go to Poker Flat in Alaska and I saw the aurora, it was very cold, but I saw the aurora for a long time. We stood outside for about 20 minutes and saw the same arc and it didn't really move very much. I'm sure if I looked at an ASI for that night, I would see some movement. They're not exactly stationary, but arcs are relatively stationary. They hang around for a long time. You can watch them a great deal. They're elongated in the east-west direction, and it's usually horizon to horizon. So the picture I'm showing at the top on the right there is actually a picture of aurora from the UK, although you have to go somewhere fairly extreme in the UK in order to be able to see it. So that arc was observed from the Isles of Shetland. But yeah, they're elongated in the east-west direction, but very narrow in the north-south direction. And so when I say narrow, if we map the width of those arcs in the ionosphere, then they're sort of 1 to 10 kilometers wide, that kind of thing. So you can see in the 3 all-sky images, which are those round images, to the bottom of the figure there, that the arc is kind of showing as this elongated feature here, and then we have other features in the other 2 pictures that are either north-south and probably part of a much more dynamic feature, and then there's a much more diffuse feature in the final one on the right, panel F, if you like. And so the arc, as I say, elongated east-west, very narrow in the north-south direction. What do we think are causing auroral arcs? Well, I actually included this physics first because it's, you could say it's an ongoing research question. They are related, when we get onto the acceleration mechanisms, they're related to quasi-stationary acceleration mechanisms for the very reason that they do appear to be effectively stationary. Whatever your acceleration mechanism is, it's going to be narrow in the north-south direction, but elongated in the east-west direction, obviously. And these arcs are often green, so you have to be able to accelerate at least a keV electrons, really, in order to be getting down to those altitudes that are causing the green aurora. So my diagram here on the top right is a quite simple diagram, but in many respects is showing us where we're at with auroral physics in terms of auroral arc physics. We basically have, in the magnetosphere, a region which generates the acceleration mechanism. So there's a generator region here, there's something that's going on that we will find out later on in the seminar is causing a potential drop along the field lines. It's connected to the ionosphere where the aurora happens by an acceleration region. And again, I'm going to talk about that when we talk about acceleration mechanisms of what could be going on in that acceleration region. But I won't lie, even in this review by Borowski et al., which is in a recent space science review from this year, we have some good theories as to what's going on that's causing the auroral arc, but I wouldn't say that we've solved the problem yet. So there's some suggestions that high latitude arcs could be mapping to the plasma sheet boundary layer or the low latitude boundary layer. Effectively, when you have a generator region, you're looking for somewhere with gradients. Gradients perpendicular to the field, often a region where you've gone from one plasma regime to another. And low latitude arcs, then some of the suggestions as to what could generate a low latitude arc are related to, again, to pressure gradients occurring across the field, or potentially stationary Alfvén waves, which is something that Dave Knudsen has proposed. But I would definitely say that this is not a problem that's been solved yet, although it's really interesting. How can you create this feature that doesn't move for, for minutes at a time, but that, as we will see later on in the seminar, is definitely associated with kinetic physics. Next, I want to talk about field line resonances. These are a series of discrete arcs, but they do move. We can sense them moving. They can move slowly polewards or equatorwards and then be replaced by another arc. And they are a manifestation of field line resonance in the magnetosphere. So I've got two examples here. One that is a poleward moving auroral form that Robert Rankin showed in 2005, and then an equatorward moving form on the dusk side that Lisa Badley showed in 2017. There's also polar cap aurora. These are also known as theta aurora or transpolar arcs. I'm not going to focus a great deal on these. They're large scale features, so you can't see them with a single all-sky imager from the ground, something that is best appreciated from space. They have been shown to predominantly occur during northward IMF periods, which have a strong northward IMF and high solar wind speed. And if you're interested in them, I can recommend the review by Hosokawa in Space Sciences Reviews. Patchy aurora are more of a diffuse phenomenon, not a discrete phenomenon. So they are more regular sized patches. When I've seen them from the ground, it's like there's a patch of the sky and someone's playing with a light switch. It goes on and off irregularly, not in a sort of periodic fashion. These are often a post-midnight phenomenon. And as I say, they're usually described as being diffuse aurora, although there are structural features. And these can occur in a range of scales that's shown in this paper by Shikawa, where there was large scale features that you can see in the all-sky imager at the top, and then these much smaller features that are pointed out by the arrows that are occurring in a much smaller field of view. And it brings me to something that I find really fascinating about the aurora, which is basically the more and more closely you look at aurora, the more and more structure you see. And I can think of no better evidence for this than a paper written by Neuropartemis in 2010, and I'm showing the histograms on the left-hand side of the slide. And basically the histograms are showing the width of auroral arcs when viewed in different cameras. The different cameras have different sizes of field of view, different pixel sizes. So obviously the range of widths that you could possibly detect with the different cameras changes. It's unique to each camera. And when you put all the results together, there's results from one camera here that's shown in blue, another one in red, another one in black, and then there's a tiny set of results here, which are a few events, a small number of events from a different green camera. But basically the point is that you can see different auroral arc widths depending on your pixel size. So all of these widths exist. It just depends on what you use to look at the aurora as to what kind of width that you will see. And so there's other examples on this slide as well of people using very, very narrow field of view cameras to show us just amazing sort of 100-meter structure in the ionosphere of the auroral arcs. What else was I going to talk about in terms of morphology? We have this pulsating and flickering aurora. So this, again, is a type of diffuse aurora, and it's related to the patchy aurora that I was showing in a previous slide. But these are auroral forms that change brightness much more regularly. Pulsating aurora has periods of roughly 2 to 20 seconds, spatial structure maybe 10 to 200 kilometers, whereas flickering aurora is the stuff that's going very fast. In order to see flickering aurora, you have to have a high cadence camera. And I can also recommend another really good review that's just come out about pulsating aurora, and that's by Nishimura et al. And you can see some examples of that type of aurora on this slide. We believe pulsating aurora is most likely related to wave-particle interactions in the magnetosphere, and I really love the plot here from Kasahara et al., which is a recent Nature paper, where they showed some data from the ERG or Arase satellite, and showed, so the top panel is showing Whistler mode waves and its paraspectral density of those waves. So the red blotches there where you're seeing increased activity of Whistler mode waves. And what they have on the two panels below are the precipitating electrons and the trapped electrons. And in the precipitating electrons, you can see enhancements in that precipitation that match up really very well with the periods of enhanced Whistler mode waves. And I think this is excellent evidence to show us that wave-particle interactions are really important for the pulsating aurora. So finally, in this little section, I want to talk a bit about substorm aurora, because without looking at the aurora, we had no working definition of the substorm, and it's really the substorms were originally defined by the auroral activity that we could see. I always think it's amazing that Akasofru put together this picture of the aurora that you can see drawn in the center of the slide there by sitting in the same spot in Alaska and looking at the sky night after night after night and putting together this global picture of the aurora, which it turns out is actually what happens. So you have those diagrams in the middle showing how a substorm works, which is basically you get a sudden brightening of the aurora, which you can see in the sort of top right sketch. So the most equatorward arc suddenly brightens. It has rapid apparent motion polewards. The whole auroral display rapidly brightens and rapidly fills the sky, showing complex patterns. And then during the recovery phase, you get more of the kind of discrete patchy aurora that I was talking about earlier. And as I say, it amazes me that someone put that together from the ground before the advent of these images that you can see at the far right of the slide that show what really happens when you look at it from space. In more recent developments, and I felt like I should add this because it's something that I've been working on too, is showing azimuthal structure in the auroral arc, this most equatorward onset arc of the substorm aurora in the 5 minutes surrounding onset. And so I'm showing on the right-hand side here the cumulative probability that an arc will show this azimuthal structuring within a few minutes of substorm onset. The substorm onset here, which is the red dashed line in the middle of the plot, was independently identified from ground-based magnetometer data, whereas the auroral structuring is obviously obtained from some camera data. By substorm onset, 70% of the arcs that were visible, that weren't behind cloud, were showing azimuthal structuring, and that grew to 90% within 3 minutes of onset after the substorm onset. And so this azimuthal structuring is clearly something related to substorms too. So after talking about the shapes of auroral displays, I want to talk a little bit about the acceleration mechanisms that we think are going on in the magnetosphere to cause the aurora. So in order to make aurora, we have to somehow get electrons from being trapped in the magnetospheric field to precipitating into the upper atmosphere. So the diagram I'm showing in the middle of the slide is showing trajectory of a trapped particle bouncing between hemispheres. This is the typical state of electrons in the magnetosphere. And this is what the distribution, if you sort of visualization of what the loss cone would look like in parallel velocity versus perpendicular velocity. So all of the electrons that are bouncing between hemispheres there are going to be mirror trapped in this diagram, the 3D diagram at the bottom. And anything that enters into the loss cone will precipitate, will take part in collisions with the neutral atoms and molecules in the upper atmosphere. So we have to do something to move electrons into this loss cone in order to help them make aurora. So what you can see on the right here is some data from the FAST mission, which is showing this kind of loss cone feature on the left-hand side here, where there's a lack of electrons inside this loss cone. Now this is only 2D, whereas this kind of diagram is 3D. But you can see that there's a lack of electrons sort of in the upwards direction here, in the parallel velocity direction. But here's some auroral electrons, because these are inside the loss cone. So FAST is going above the atmosphere at about 1,700 kilometers altitude. And the electrons it's seeing on the right-hand side of the image are the ones that are going to be taking part in collisions underneath the spacecraft with the upper atmospheric constituents. So how do we get them in, how can we get electrons that were originally trapped and move them into the loss cone so that they can cause aurora? So there's two main classes of auroral acceleration mechanism, and in terms of physics, they're fairly straightforward. The first two there, the quasi-static potential drop and the broadband dispersive alpha wave type acceleration mechanisms, these cause discrete aurora, and all that's really involved is finding a way to create a parallel electric field. So that's an electric field directed along the local magnetic field direction in order to create a force that pushes the electrons into the loss cone. So it's fairly straightforward. You just need a parallel electric field. Then you have pitch angle scattering, which is one of the things we think causes diffuse aurora. And it's kind of a non-traditional acceleration. You don't get an increase in energy, but you do get a change in the pitch angle. And so there's no change in energy here. All you do is move the pitch angle of a particular particle through a wave-particle interaction and move it into the loss cone that way. So what I'm going to focus on for the rest of the talk are these two up here, the quasi-static potential drop and the broadband or dispersive alpha wave mechanisms, and basically discuss how you can create a parallel electric field. So first of all, let's think about a quasi-static potential drop. So this is inferred from behavior of electrons that are seen on low altitude platforms such as DMSP or FAST or Freya or rockets or any of those things. So we see this in this image here. We've got, as a function of time, the third panel shows the electron differential energy flux. And you can see what looks like a rise and then fall. There's this kind of monoenergetic acceleration here. And these are known as inverted V structures. They're long-lived if you compare them to the electron bound period, but they're not truly static. And we're inferring that there's the presence of an electrostatic potential difference that is greatest in the direction along the field line. That's creating your parallel electric field. So if one was to fly some spacecraft through, that is depicted in this image here, these are two cluster spacecraft flying through what we think is the potential structure during the time the measurements were taken. Then the inverted V structure happens because the spacecraft are flying through what is a U-shaped potential. The gradients along the field can be both sharp and weak. So you can have mixtures of potential gradients that are quite weak, and then you might have it all collected together that's shown in the bottom of the diagram here, where there's a sort of low altitude double layer, that's what it's called there, but it's a region where the potential gradient is very strong. So these sharp parallel gradients can exist as double layers, as a region of charge separation, and they can also move and change strength in sort of second timescales. And so this is not a static picture at all. The sort of traditional picture of the auroral acceleration region is that it's occurring somewhere between, say, 1800, 1900 kilometers or so, and maybe 10,000 kilometers. It's bounded by two strong double layers. But it's likely to be much more complicated than this rather simplified picture is suggesting. As I say, these double layers can move up and down, they can change strength, and in order to solve this or find out more about this, it does point to the fact that multi-point measurements are essential. FAST was an amazing mission and we learned an awful lot about auroral physics, but wouldn't it have been great if there'd been more than one of them so that we could look at this potential structure along the same field line. There has been lots of theoretical work on what the structure looks like. So here we've got examples of U-shape potentials and S-shape potentials, and reasons for potentials changing from one to the other. So the first U-shaped potential was inferred by the perpendicular electric fields, which are pointing towards one another. So when you see that, you can infer the existence of a potential of a U-shaped potential underneath your spacecraft. And then when the next cluster spacecraft came through exactly the same region, it didn't see the kind of the electric field pointing towards the structure from the left-hand side. It only saw the electric field pointing towards the structure from the right. And so this is implying that the potential structure is changing. The other type of auroral acceleration mechanism that we might want to consider is, or another way to create this parallel electric field is something known as broadband or shear Alfvén wave acceleration. And so again, if you look at the differential energy flux, the acceleration is occurring over a much wider range of energies. So it's not that tight inverted V shape anymore. The acceleration is happening over a wide range of energies. And these signatures are often related to Alfvén wave measurements, and they've been seen at low altitude and at high altitude too. How can we support a parallel electric field in a shear Alfvén wave? I've got a lot of information on this slide, But basically, the idea is that usually you have a shear alpha wave as is in the diagram I have here on the right. So it's a wiggle in the magnetic field, and it's they are non-compressional waves, so there's no density perturbation. And in the MHD limit, a shear alpha wave propagates exactly along the field. But if you introduce a finite K-perp, so you have some kind of perpendicular scale, then the waves have to support a parallel current. And they do that through the continuity equation that I'm showing on the bottom right. So the incompressible continuity equation implies that div j is going to be equal to 0. If I split that into components for perpendicular and parallel and kind of solve for the j parallel component, it's telling me that it's proportional not just to the perpendicular component of the current, which is a signature of the wave, but also on the ratio of the perpendicular scale to the parallel scale. So basically, if I can increase my perpendicular scale, if I can decrease my perpendicular scale and increase my perpendicular wave number, then it allows me to, means I need a parallel current to support that wave. And if I need a parallel current, then the only way to do that is to have a parallel electric field that pushes the electrons up and down the field in order to create that parallel current. So basically, short perpendicular scale, big perpendicular wave number, gives you a paraelectric field in your shear alpha wave. And this is what we think is happening above the aurora. Let me move on. There are different regimes in which this paraelectric field can exist. So you can have a situation where your thermal speed, your electron thermal speed, is much less than the local alphane speed. You can also have a situation where it's much more than the local alphane speed, or it could be roughly the same. In one of these situations where the thermal electron speed is much smaller than the alphane speed, then we're in what we call the inertial regime. This happens at low altitude. And in these circumstances, then you can get a sizable paraelectric field if your perpendicular wave scale is comparable to the electron skin dip. The other end of the scale, if your electron thermal speed is much bigger than the alphane speed, then you're in the kinetic regime. This is where electron pressure is taking over, and you can get a sizable paraelectric field if your perpendicular scale is comparable to the electron skin depth times the thermal speed divided by the alphane speed. If you're somewhere in the middle, sadly, you don't have any of these nice easy equations to figure out what your paraelectric field is. You have to go to the full complex solution of the dispersion tensor, and there's instructions for that, and Liza can log it, thankfully. But you do get, you still get a paraelectric field in these circumstances too. The thing is that we're going along auroral field lines, then we move from the kinetic regime to the inertial regime. So in this diagram here, where I've selected part of an auroral field line stretching from this end, which is sort of between x equals 6 and 8 RE there, which you can imagine being close to the plasma sheet or the plasma sheet boundary there, where you have warm plasma. That's going to be where the thermal electron speed is much bigger than the alphane speed. As we get closer to the Earth, though, if the alphane wave is traveling along the field line down towards the ionosphere, then close to the ionosphere, we're going to be in the inertial regime, where the plasma is cold. The electron thermal speed is much less than the alphane speed. So what kind of electric field you can support kind of comes down to where does that shear alphane wave develop the small perpendicular scales. And there's many different ideas as to where this could happen. It could happen in the plasma sheet boundary layer due to the density gradients. It could happen as part of a turbulent cascade as the waves propagate. Or it could happen in the traditional auroral acceleration region because you've got density cavities there. And maybe the short perpendicular scales arise due to those density gradients. This motion from one regime to the other changes the form of the acceleration. So at high altitude, we were seeing in numerical experiments that you get sort of nonlinear trapping within the waves. So the kinetic regime was giving you a good E parallel, and it was accelerating some electrons that were getting trapped within the successive E parallels of the wave. And then as the wave moved further down the field line towards the colder plasma, the more inertial regime, then the E parallel would be decreasing, and what happened is the electrons could then stream down the field line in order to cause the aurora. If the short perpendicular scales do develop at high altitude, then we managed to find out from the numerical experiments that we could see sort of an elongation in the electron distribution. So in the pictures here, I'm showing at the bottom something from numerical experiments. So this is a simulation of the shear-offing wave electron interaction. And then the two pictures at the top there are showing data from the polar spacecraft, showing this elongation of electrons, the electron distribution function at low energy. It's only happening at low energy, which is suggesting that it's a wave-particle interaction that is involved. If the short perpendicular scales, on the other hand, develop at low altitude, then we're seeing these energy dispersed features in the auroral electrons instead. So here on the left is an image from a Chaston et al. Paper. So you've got electron energy on the left as a function of time, and you can see the energy dispersed feature there. And we also managed to reproduce that kind of feature in numerical experiments too. I wanted to highlight the occurrence of these different discrete auroral types because you can tell them from the differential energy flux data. And so highlighting this paper by Park et al. Is indicating in these plots the characteristic energy of monoenergetic or the parallel drop type of parallel potential drop kind of acceleration mechanism, and then the broadband or shear-offing wave acceleration mechanism on the right. And you can see that the characteristic energy is slightly higher for the monoenergetic acceleration, and there's a bit more flux involved in the monoenergetic acceleration, which is a result that was also found by Newell et al. In 2009. What interests me a lot is the difference between the pitch angle behavior of these discrete auroral acceleration mechanisms. So, I mean, monoenergetic acceleration, which is what's being shown on the top of this image, is always broad in pitch angle. And in fact, it peaks away from the field line direction and nearly at the perpendicular direction. Broadband acceleration, on the other hand, is sometimes broad in pitch angle, not all the time, but sometimes, but it always peaks in the field line direction. So it's very interesting to sort of compare and contrast the behavior in pitch angle as well. I am sorry, I'm going to skip over that slide just so I can get to this before the end. The auroral acceleration near substorm onset is just something I wanted to highlight before I finish this seminar. And I wanted to talk a little bit about the evidence for this shear-offing wave acceleration mechanism in the substorm onset aurora. So first of all, I want to share with you a plot from Mendy et al. Paper in 2003, which was kind of the first in situ evidence that the substorm, sort of the auroral onset arc, is associated with this shear-offing wave mechanism. So at the top, there's some image observations. Image was a satellite that was taking obviously images of the aurora, and you can see the auroral oval at the top there and how it develops during the course of the substorm. But at the same time, the FAST spacecraft was orbiting just above those auroral forms, and you can see very much a very brief burst of broadband aurora happening between those two dashed lines in the plot. And you can see that the enhancements are happening across a wide range of energies. And at the same time, the electromagnetic field observations are kind of indicating that we might be seeing a shear-offing wave related acceleration process. So why would shear-offing waves be involved with substorms? There's been a long association between ULF waves and substorms. And I am aware that ULF waves are not necessarily shear-offing waves, but I'm hoping to show you a bit more evidence in the next few slides. These slides are images where if you look at the ULF wave activity on the ground, so all of the little yellow stations there are ground-based magnetometer stations, and you see when that ULF wave activity starts to build beyond the background, and then you plot that using contours to show when it starts building above the background, and then compare that to the location of the aurora. You can see that the ULF waves and the substorm onset aurora are happening at the same time and in the same place. And so this is a good piece of evidence too. We also saw that the ULF wave growth that's happening at substorm onset that you can see very clearly on the ground is happening in space too. So this is an example of some in situ themis measurements where you see exponential increase in brightness of the aurora, exponential growth of ULF wave power, and both in ground and in space. And Andy Smith here found over 170 events with similar growth characteristics. So we're seeing this ULF wave power in many places. You can see the structure in the aurora that I was talking about, and we can show that that structure grows. And you can see that it grows exponentially, and if you resolve it into different wave numbers, then they're all growing with different exponential rates. And sorry, I'm going to skip all the way through to here, which is an analysis that Nadine Kalmoni did, where she looked at the temporal variation of the aurora and changed it into frequency, which is what you can see on the vertical axis. And the azimuthal structure of the aurora in the east-west direction, changed that into a wave number, which is what you can see on the horizontal axis, and then compared that with solutions of a shear Alfvén wave dispersion relation. And we found that they matched really well. The solutions here are shown with sort of error bars, if you like, where we're just trying to show how whether those solutions were sensitive to our initial choices of things that were happening in the plasma sheet. And they're not sensitive enough that I would say that that would make too much of a difference. So the aurora itself is telling us about the wave-particle interaction that we think might be causing it. So there's my conclusion for the substorm aurora, and I'm painfully aware that I'm probably over time. So I'll leave that for people to look at later and hop straight on to my future thoughts. Which is that auroral physics are fascinating and very rich field of study, and there are many remaining unanswered questions. What supports auroral arcs feels like one of the most obvious questions that you could ask, and yet it's difficult to perhaps distinguish between some competing theories. What's the relationship between one kind of auroral acceleration mechanism and another one? I would love to find out what controls the shape of patchy aurora, and all of the different questions that are brought up by this relationship between ULF waves and substorm onset aurora, you know, they need answering too. And so what I wanted to leave you with was the idea that we need two things, and that those two things are quite hard before we can really answer these questions. But the first thing is that we need multi-point observations in order to answer the questions. They need to be along the field and across the field. And that the electric field is such an important observation to make, because that will be the key to distinguishing between competing theories. And that we need kinetic modeling of large-scale Magnetosphere coupling, which, as I'm sure many of you can appreciate, is a very difficult thing to do. But if we can do either of those things, or maybe both, then there are ways to answer some of these deep and fundamental questions about aurora. So thank you very much, and I look forward to your questions.
Thank you, Claire. That was very interesting and very clear talk. We have many questions.
Great.
But before, once you have a big audience, I want to remind you that next Monday we have Dr. Eric Donovan, and he will talk about the quantum aurora. So yeah, I look to see you all here next week too. And so let's go to the questions. The first one is from Krishna Chandra, and it was around slide 17. And he's asking how the stationary Alfvén waves are responsible for the formation of the auroral arc.
So I was talking about later on about here maybe, yes. I was talking later on about how paraelectric fields are associated with shear Alfvén waves that propagate. But the stationary Alfvén wave idea is simply, if you were to allow the frequency of the Alfvén wave to tend towards zero, then the same properties still apply. You still need if the Alfvén wave has a short perpendicular scale, it still requires there to be a parallel current element, and so it will need a paraelectric field in order to sustain that parallel current element. Now, in some cases, I've heard people suggest that the stationary Alfvén wave idea is just one way of thinking of a quasi-static potential drop. But it is more than that, because the alpha wave itself organizes the magnetic field perturbations and the electric field perturbations that are going on perpendicular to the field as well. And so I would encourage you to look up that Knudsen paper from '96. Actually explains it a lot better than I could. Effectively the same physics is applying here. If you have a short perpendicular scale, whether your shear alpha wave is propagating, standing, or stationary, i.e. at the zero frequency limit, then you need a paraelectric field to sustain the parallel current part of that wave. And so it's the paraelectric field that's so important for auroral acceleration. And so that I hope answers your question. Okay.
Thank you. So, and the next one is from our colleague Ankush. He wants to know how the polar cap occurs, and he asks you for more details.
I love when people ask me things about stuff I'm not that expert on. My understanding so far is this, that during periods of northward IMF, the reconnection that's happening between the solar wind and the magnetosphere is no longer happening at the subsolar point. It could be happening at higher latitude. And so as a result of this kind of higher latitude reconnection process, you begin to see auroral features going across the auroral cap, so the polar cap, and this is what's causing them to light up. And much beyond that, I think I'd have to direct you to that Hasakawa review.
Yeah, so you can get all the reference from your talk later. Thank you. And from Jinxin Li, around the slide 14, so why did sweet aurora exhibit the vortex structure?
Oh, why do aurora have the vortex structure?
Yeah.
Right, that's a great question. It's actually related a bit, I think, to the relationship between the aurora and ULF waves. And so this isn't true for all vortices, but some of the vortices I've seen that have grown out of that azimuthal structuring that happens near substorm onset, they kind of end up wrapping themselves up into vortices too. And it's sort of what we think is kind of the progression of the waves as they're growing. So there's evidence that the waves are growing in size, and they're growing exponentially, and then they reach a point where they begin to wrap up into smaller and smaller vortices. Now that's not the only way that an auroral vortex or an auroral curl can exist, and I apologize profusely, but I don't actually remember any of the other theories. I would encourage you to look up the literature on auroral curls as well, because that's another terminology that people have used to describe them.
Okay. Thank you. And see here. The next one is from Jason Durr, asking how does the aurora arc morphology and the slide 20 follow a special power law of some sort? And is there a fractal dimension associated with the structure of events?
That is a brilliant question. Now, part of me knows of some studies that have been done on power laws, but not on structure, on brightness. Back, gosh, maybe 20 years ago now, Sandra Chapman, Nick Watkins, and others were doing some work looking at the amount of brightness in a particular auroral form, and they found that there was sort of power laws if you plotted the distribution of auroral brightness and size of auroral blob. But they were doing it from space-based cameras, right? So you're limited there by the size of your pixel. But doing the same study from the ground would be very interesting, because obviously you've then got, you can only possibly look at maybe 1.5 orders of magnitude with a single camera, because you've got limits, like most cameras are maybe 256 pixels by 256. So there's a limit to the sort of biggest scale and smallest scale that you can detect with a single instrument. Has anybody done it over larger orders of magnitude? I don't think so, but I'd love to see it if they had.
Okay, thank you. And moving on, again from Ankush, and asking how the V-shaped potential forms and not causes its motion on slide 32.
So, sorry, could you repeat the question, please?
Yeah, how the V-shaped potential forms and what causes the motion.
Ah, right, yeah. So about the V-shaped, like the inverted V-shaped auroral forms is on, that was on 28th, though you said slide 32. So I just want to make sure I'm answering the right thing. So the inverted V auroral forms we think are associated with those kind of more stationary auroral arcs, the motion of spacecraft or rockets or whatever through in the horizontal direction through the potential drop is what we think is showing this inverted V. Because if you imagine in this picture with these gray auroral magnetic field lines, the way that the potentials are drawn here, then the potential difference along the side of the U-shaped potentials, if you like, is weaker than it is in the middle of the U. And so the electrons wouldn't be accelerated to as high energy, sort of as you're going through the sides of this U-shaped structure, as when you're going through the middle of it. If we're looking instead at slide 32, where this is a more broadband shear-off wave acceleration mechanism, then I must admit that the way that this broadband acceleration is associated, we think, with much more dynamic auroral forms, still discrete forms, but much more varying dynamic forms. And I genuinely want to see multi-point observations, you know, sort of one spacecraft following another through this to see how it evolves, because I think that's a really good and unanswered question.
Okay. So also related to the inverted V, from Lynn Wilson, asking if it looks like the units of the phase space density, the electrons, the velocity distribution function looks like in the unit of the phase space density, not energy flux.
Yes, so I checked this when I put it on the slide, and I'm fairly sure it's showing differential energy flux, regardless of what the
I was asking about the the inverted V and energy flux looks like there's a dearth of electrons at lower energies, and I was wondering if that apparent dearth is a consequence of the units or if it's a real thing, like what if you show phase space density, I thought you still see like a lot of electrons at lower energies.
Yeah, you're absolutely right. If one was to show these as a function of phase space density, then what you're more likely to be seeing is like a ledge in the distribution function or in the phase space density, and not this kind of peak in the differential energy flux. So this only really, when you see the observations of the aurora, it tends to be in this form, because then you can pick out, it basically allows you to pick out the characteristic energy of the accelerated form easier, right? Because you're seeing something that's what, E squared times phase space density or something like that. So if you were to look at this in phase space density, then you're pretty much seeing either a ledge or maybe a slight bump, but you know, it'd be very, very kind of minor, very subtle effect. So yeah, usually the DMSP or the fast observations are showing differential energy flux, because it's very easy to eyeball that and say that I have roughly 10 keV at its peak characteristic energy, because you know it's going to show up clear as day in the differential energy flux.
Thank you, Lynn. And another question from Jason there. In the analysis performed by Dr. Kalmoni, in the end of your talk, I believe, the growth rates were obtained by a feeding of the log of the power spectral density to a linear feed.
Yeah.
But how is it determined which portion of the growth is linear, since higher order non-linearities could be involved in the growth?
Great question. I wish I had, I have the plot, and that's slide I skipped. Sorry, I'm just going to go through the slides, see whether I have the plot. This one, no. Yeah, yes, no, it's a really good question. So when Nadine did this analysis, basically if you can focus on the this panel here that's showing, can you see my mouse, by the way? Because I keep hoping that you can. This sort of second big panel here that's showing the longitude on the vertical axis as a function of time. And the color thing that's being showed here is the brightness of the auroral form once it's been decomposed into azimuthal wavelengths. And so you can see, obviously it's very dark here, and then you can see the growth of these features. And what Nadine did is take horizontal cuts through every single part of this figure and plot it as a time series. And for the first couple of events that she chose, she did it by eye to identify a period that appeared to be growing, being a linear line on an exponential plot, which is a sign of exponential growth. And then for this particular paper, she developed an algorithm that would spot it. So it's effectively taking the peaks of the line, because they tend to be bumpy lines, you know, kind of oscillating lines. She developed an algorithm to take the peaks of that and then fit a line to it in log-lin space. And there were rules on the on how good a fit it was before she accepted it. And so that's how that worked. But in the beginning, there was a lot of looking at the time series, and you can see noise and then exponential growth. And then afterwards, when obviously saturation of whatever's going on is happening, you don't fit a line to that part. And so hopefully that answers your question.
Okay, thank you. And from Dobkan Osterg, asking if can multi-point magnetic field measurements also help with the understanding of the role of SAW?
Yes, absolutely. So multi-point measurements, I think, well, obviously it depends from what platform and how close they are together. But if you have a multi-point magnetic field measurement, that tells you something about the current systems. One of the wonderful things that Cluster did is it had 4 magnetic field measurements. Well, obviously it has 4 spacecraft, but it had 4 magnetic field measurements. The spacecraft are flying in a sort of tetrahedral formation. And if you take the gradients of the magnetic fields between each of the spacecrafts, you can effectively use curl B equals J. And it gives you an estimate of the currents that are happening. So if you had multi-point magnetic field measurements that were close enough together, then that gives you an indication of what electrical currents are happening. So both in the parallel and the perpendicular direction. And so many of our models of the electron acceleration mechanism are related very heavily with the electric fields and with the currents. And so having an insight into that picture would be really great. And some of the work I didn't have time to show is various rocket campaigns where people sent up a payload that then had maybe a mother and some daughter small payloads, or were kind of nanosats or something like that, where there are multi-point measurements, and quite close together. And so they had that magnetic field measurement and the estimates of the current. And I think, names are just, sorry, the name was on the tip of my tongue, but there is a rocket measurement I remember quite closely because it did show sort of a really good estimate of what the parallel current strength was above the aurora. I'll remember it once we've stopped this call.
Okay, let's move on. And from Aaron, could you explain more about the turbulence cascade idea for shear offing wave perpendicular scale growth? In the case of FLRs, does that mean higher order harmonic resonance coming into play?
So as far as I remember from Chris Chastan's work, he was looking specifically at propagating shear-Alfvén waves and not standing ones. And so the idea is that something further down tail is creating shear-Alfvén waves, and perhaps it's creating them with quite large scales. And then as the waves propagate towards the ionosphere, you have that perhaps the origin of the waves is maybe a broad band, it's not monochromatic. And so you end up with this kind of energy feeding from the larger scales down to the smaller scales in a regular turbulent cascade. And the reason why turbulence became a good description for this is that when in the Chastan et al. Work, when they looked at the kind of power law of the perpendicular electric field perturbations and the perpendicular magnetic field perturbations as a function of the implied perpendicular scale length, they had the right sorry, I'm trying to throw that phone out. Sorry, what was I saying? They had the right power laws in the turbulent cascade, that it was likely that they had the right power laws when they looked at the perpendicular electric field perturbations and the perpendicular magnetic field perturbations, that it looked like it was turbulent. But exactly how that happens above the aurora is not known yet. And the other thing we have to remember is that there's lots of these density gradients happening across the field. So if your field line maps to, let's say, the boundary between the plasma sheet boundary layer and the central plasma sheet, or it's mapping to somewhere that has a steep density gradient across the field, then that could be imposing scale sizes as well. It was just that when Chris Chastan did this work and he looked at the power law of the perturbations, it looked turbulent.
Okay, thank you. And the last but not least, again from Krishna Chandra, as the parallel electric field is responsible for these particle accelerations, the kinetic Alfvén wave is also associated with a parallel electric field. What kind of aurora is produced due to the presence of kinetic Alfvén wave?
It's a really good question. So, I mean, if the kinetic Alfvén wave is producing aurora, then we would imagine that the kind of aurora it's producing would be modulated at least at the frequency of the waves, which is one of the reasons I was associating with them these azimuthal kind of auroral forms close to substorm onset, because they change both in spatial structure and in time. And so you can see that kind of frequency modulation, and in fact is the reason, says very quickly going to the plot, is the reason why we could extract this omega k relationship from the aurora itself. And so it's modulated in time and in space with the same characteristics as a shear Alfvén wave in the kinetic regime, so a kinetic Alfvén wave. But if we're looking away from substorms and looking at other kinds of forms, then there's definitely lots of suggestion that, say, field line resonances giving you aurora might be sort of field line resonances that have these short perpendicular scales, so we're in the kinetic regime. And if you were, there's a lot of evidence from Weigand et al. And Keiling et al. Over the course of, I'd say, 2 decades, indicating from polar observations that there's at least enough power in the shear Alfvén waves to power the aurora. But then what they would look like, as I say, I think that they would be modulated at the kind of frequencies that the kinetic Alfvén wave is modulated at. So you wouldn't be talking about a persistent auroral arc. You'd be talking about an auroral form that was more dynamic, and that perhaps had some of these more wave-like features in it. And so that's, I think, most likely from this acceleration mechanism. Okay, so thank you very much. That was a very interesting talk, very interesting questions from everyone. So yeah, thank you again. So I hope to see you all on next Monday.
And again, Eric Donovan, you talk about proton aurora. And yep, thank you, Claire. Thank you all.
Thank you.